Okay, so in this lecture we show how to obtain the three-term recurrence relation corresponding to Laguerre polynomials starting from first principles. So Laguerre polynomials are obtained when we set s of x to be x, w of x the weight function to be e to the minus x, and the interval corresponding to Laguerre polynomials is from 0 to infinity. We have seen this, and the Rodrigues formula corresponding to Laguerre polynomials is e to the x divided by n factorial times nth derivative of the product e to the minus x times x to the n. And so this will give us Laguerre polynomials for all integer values starting from 0, 0, 1, 2 all the way up to infinity. You can keep on increasing them. And we have also seen how we have this orthonormality condition, integral 0 to infinity dx e to the minus x lm of x times ln of x is equal to just the Kronecker delta mn. Now in this lecture we will work out the three-term recurrence relation. So the general three-term recurrence relation is of this form, right? So ln plus 1 of x minus some coefficient alpha n times x times ln of x is equal to beta n times ln of x plus gamma n times ln minus 1 of x, right? So in the case of Hamid polynomials and in the case of Legendre polynomials, we argued that this coefficient beta n is going to go to 0 because of their well-defined parity for each of the polynomials, and also the fact that this parity would oscillate, right? So you would get either even polynomials or odd polynomials depending on the the term that you're considering, the member of the sequence, right? If you started with 0, you would get an even polynomial, n equal to 1 would give you odd, and again back to even, and so on. But we have seen that Laguerre polynomials don't have definite parity, so this argument does not hold anymore, and therefore we have a full genuine three-term recurrence relation. So we'll have to work out all these three coefficients, alpha n, beta n, and gamma n, which is what we will do in this lecture. Okay, so we start with the Rodrigues formula as usual. Ln of x is equal to e to the x divided by n factorial times the nth derivative of this product, and then we quickly write down the the highest order term in this. It's because it's going to be useful in a moment, as you'll see. So the highest order term is obtained when all these derivatives are taken only with respect to e to the minus x. So x to the n is left as it is, so it's an nth degree polynomial. So the highest order term is going to be when you just have minus 1 to the n and divided by n factorial, basically, right? So the highest order term's coefficient is minus 1 to the n divided by n factorial. We have already seen this when we were working out the normalization integral. Now, from a few lectures ago, you'll recall when we were discussing orthogonal polynomials from a general perspective, the way to get this coefficient alpha n is to take the coefficient of the highest order term in ln plus 1 of x and then divide it by the corresponding coefficient, the highest order coefficient in ln of x. So which we are ready to do. So alpha n is simply minus 1 to the n plus 1 divided by n plus 1 factorial divided by minus 1 to the n divided by n factorial, which we can write it in this manner. And so we have cancellations which happen here. So n plus 1 is the only thing which will survive, because you can write the denominator as n plus 1 times n factorial, and n factorial cancels, and together this minus 1 to the n plus 1 divided by minus 1 to the n is of course just minus 1. So alpha n is immediately seen to be simply minus 1 over n plus 1. Therefore our recurrence relation also already has this form which is becoming more and more concrete. So ln plus 1 of x is equal to minus 1 over n plus 1 times x times ln of x plus beta n times ln of x plus gamma n of times ln minus 1 of x. So now there are these two coefficients beta n and gamma n which need to be worked out, and to do this we will exploit the orthonormality properties of the Laguerre polynomials. So what we do is we multiply throughout with ln minus 1, tag the weight function along and integrate. So when we do this, the left hand side, ln minus 1 and ln plus 1 are by design orthogonal to each other. So when you do this integral on the left hand side, it's going to be just 0, and then we have this integral minus 1 over n plus 1 times 0 to infinity x times, dx e to the minus x times ln of x times ln minus 1 of x plus Again, we can argue that ln and ln minus 1 are orthogonal to each other. So the second term also will vanish. It's only the third term which will stay. So we have, but the third term is again something which we already know. So the normalization integral is just 1 because ln minus 1 appears 2 times. So that's the third term can be simply written as gamma n times 1, which is gamma n, right? So we immediately have an expression for gamma n, right? So we can bring this gamma n to the left hand side, and I mean, just take care of the signs properly, and so we have 1 over n plus 1 times integral 0 to infinity dx e to the minus x times ln of x times ln minus 1 of x, right? So although we have this gamma n in terms of an integral, we need to also work out what this integral is, right? So that we write down an answer for it. And so let's do this integral again, in a clever way. So to do this, what we will do is we will first multiply equation 1 throughout, not I mean, instead of multiplying by ln minus 1, let's multiply by ln plus 1 of x, and you'll see that we will be able to extract this integral. So again, we tag the weight function and do the integral from 0 to infinity. So the left hand side, it's a normalization integral, so it just goes to 1, and then we have minus 1 over n plus 1 integral 0 to infinity dx e to the minus x times ln of x times ln plus 1 of x, and then again we argue that beta this second term is going to go to 0 because ln and ln plus 1 are orthogonal to each other, and once again the third term also will go to 0 because ln minus 1 and ln plus 1 are orthogonal. So we are left with just one integral, and that integral is actually nothing but the integral we are after, except that we have to see that here we have ln of x times ln plus 1 of x, whereas here we wanted ln times ln minus 1 of x. So there is a ready fix for this, and that is to just shift n to n minus 1. If you change n to n minus 1, so this term will become n minus 1, this will become ln, and so this is going to become n here. Instead of minus 1 over n plus 1, you'll have minus 1 over n, and then you bring it to the to the right hand side if you wish, and you rearrange these terms in such a way that you write down this integral 0 to infinity dx e to the minus x times ln of x times ln minus 1 of x as just simply minus n. So this is nothing but, when along with equation 2, we can immediately say that gamma n is minus n divided by n plus 1, right? So this means that our recursion relation has become even more concrete now. So we have worked out 2 of these unknown coefficients out of the 3. So we have ln plus 1 of x is minus 1 over n plus 1 times x times ln of x plus beta n times ln of x minus n over n plus 1 times ln minus 1 of x. So only beta n remains to be worked out, and so we might be tempted to multiply throughout by with ln of x and see if it can tell us the answer. So of course the left hand side will go to 0 because ln and ln plus 1 are orthogonal, and then we will be left with this term. So ln times ln square, so you get an ln squared. So there is this integral which we'll have to work out. Beta n times this of course will just go to 1, and again by orthogonality you can argue that this term also goes to 0. But the difficulty is we don't know how to work out this integral. This requires work. So it turns out that in fact it's convenient to work out this coefficient beta n directly. We'll start with the Rodrigues formula and then use Leibniz rule. So Rodrigues formula tells us ln of x is e to the x divided by n factorial times this nth derivative of this product. Now let us work out not just the highest order term, but let's also work out the next order term. The highest order term after all comes when you take all these derivatives with respect to e to the minus x. So that's how you get a minus 1 to the n, and then e to the minus x, and x to the n remains as it is. But then the next order term will come in when you take one derivative with respect to the second of this, x to the n. So that's going to give you n times x to the n minus 1. But there are you're doing this n times. You could have chosen to do this derivative with respect to x in n different ways. So that's how you get this factor n. So, or you can directly apply Leibniz rule and say that you should get n times the derivative of the n minus 1th derivative of the first term times the first derivative of this second. So we have n times minus 1 to the n minus 1 times e to the minus x. That's the n minus 1th derivative of this function, and then the first derivative of this function is n times x to the n minus 1, right? And then there are lower order terms after that, which we will not consider now. So the coefficient of the second highest power, x to the n minus 1, is actually nothing but, if you look at this, the second term is minus 1 to the n minus 1 times n. One of these n's will cancel with the highest power here, and you have a n minus 1 factorial in the denominator. So this is the second highest power x to the n minus 1 in ln of x. So now what we will do is, we will go to equation 3, which is, this is the unknown, which we want to work out beta n, we don't know. And so what we will do is, we will compare the coefficient corresponding to the second highest order term on the left hand side and the same coefficient on the right hand side. So if you have ln plus 1 of x, it's a polynomial of degree n plus 1. So let's look at the coefficient corresponding to x to the n. So according to this prescription, it must be minus 1 to the n times n plus 1 divided by n factorial, right? So we have ln plus 1 of x, and we are looking at the nth term. So that's what this is. And then again, we have x times ln of x, right? So ln of x is a polynomial of degree n. So if you take the highest power here and multiply with x, that's going to correspond to x to the n plus 1, but that's not what we want. So we want the next order term, and that order term is exactly what we just calculated. So it's just exactly minus 1 to the n minus 1 times n divided by n minus 1 factorial. Then we have to tag along this factor minus 1 over n plus 1, because we have this factor minus 1 over n plus 1. And then we have we also have plus beta n times, this is the highest order term. So ln is a polynomial of degree n. So we are interested in the coefficient corresponding to x to the n. So that's the highest order term in here, which we already worked out. And so that's nothing but beta n times minus 1 to the n by n factorial. And the other term does not contribute, because this is, after all, it's a polynomial of degree n minus 1, and we are interested in comparing coefficients corresponding to x to the n. So this won't contribute, and all we have to do is now do some simplification here. It's just some algebra, and we can immediately show, all these n minus 1 factorials will just cancel, and you're left with n here on the left hand side. So n plus 1 divided by n, minus 1 to the n will go, and then you have minus times minus 1 to the n minus 1. So again, minus 1 to the n goes throughout. So you have n plus 1 divided by n is equal to n over n plus 1 plus beta n divided by n. So n minus 1 factorial has been pulled out throughout, and immediately we can write down beta n as 2n plus 1 divided by n plus 1. You can check this, it's some very simple algebra, and that's basically it. We just have to collect all these three pieces of information and then write down the three-term recurrence relation. So it turns out the three-term recurrence relation here is n plus 1 times ln plus 1 of x is equal to 2n plus 1 minus x times ln of x minus n times ln minus 1 of x. Okay, so that's all for this lecture. Thank you.